Okay, folks, this section of this video is going to be devoted to section 2.4, which is on distribution of data, okay? And so there's a few 2.4 questions on the homework number one that you guys are working on. I did not type any of this stuff up into the notes. There's a few vocab words, but most of them come with a picture associated with it, and so I thought this would probably be the easiest way to get this information across. In neither one of my classes did I get to cover this, so let me just include it here. And then you guys can watch this video, and there we go. Of course, you can always read the ebook. So I'll suggest that when in doubt, if you like to get ahead in a homework and you feel like we haven't covered the material yet, by all means, go into the ebook, look ahead. You can probably figure it out and do it that way. But I'll try to convey everything that we're supposed to know. So I've got three graphs here that we're thinking of sort of distributions of data. And so this one, first of all, I could call, so we're going to talk about what's called the modality of a distribution of data, all right, modality. And so this one we say is unimodal. Got one mode or style of data sort of builds up to this peak and then kind of turns down. Here I've got two peaks, so that's called bimodal. All right. And then if I've got three or more, we're going to call that multimodal. Okay. So here, the bimodal, notice I made the peaks about the same size. So this would be your, you'd have your variables here, and then you've got your frequency on this axis over here. So similar to the way that we looked at all those distributions in class. So maybe your variable is an increasing number, maybe from 0 to 100, and then you could have your frequency or your percentage or whatever type of quantity you're measuring is going up like that. All right. This has multimodal because I see sort of 1, 2, 3 peaks. So that means whatever this data value is, whatever this data value is, and whatever this data value is, are the three most common ones. And then in between there, a little bit less common, appears a little bit less frequently. Notice the peaks are not all exactly the same height. That's okay. We still call that guy multimodal. All right. Something else we're going to look at is symmetry. While we're looking at this unimodal one looks to be what we call, you might have heard a normal curve before. All right. So a normal curve is and we'll get there in the semester, but that's kind of a unimodal curve that's symmetric. And so what does symmetric mean? Symmetric means that there's kind of a line of symmetry and then it's sort of a mirror image on one side versus the other. Okay, so this one looks pretty symmetric to me. This one I aimed to make this one look a bit symmetric. This one's not, right? This one's not symmetric because if I find the halfway point, one side of it, this peak is lower than that peak. So this is, I would say asymmetric, but the book is calling it non-symmetric. But there we go. So depending on the modality is one aspect of a distribution. The symmetry is another one, and they kind of mix and match differently. So this multimodal one is not symmetric. Can you have a multimodal distribution that is symmetric? Sure. Let me try to make one. So let's say I've got a peak, and a peak, and a peak. Something like that, right? So I'm doing my best. I'm not measuring, but I've got 1, 2, 3 peaks right there. Make my little symmetry line, and that looks now symmetric. That one seems to be symmetric. Okay. So we've got modality, and then we've got symmetry. For this unimodal one, I mentioned this one is symmetric and unimodal. That's what we might call a normal curve. That's just the phrase. So you might have heard that in the past. That doesn't mean the other ones are abnormal. It's just a normal curve. You might call this a bell curve. So you've probably seen the phrase or heard the phrase bell curve before. And so a lot of data is represented as a bell curve. If you've ever taken an IQ test or you're familiar with IQ tests, your IQ is sort of a arbitrary number that's associated with your intelligence, right? And so that, in other words, it's fully human created, right? So in other words, your age, you could argue, is a arbitrary number in a way, but your age is based on how many years you've been alive, and years are based on how many times the Earth's gone around the sun. So there's really no debate on how old you are. The revolutions of the sun to say it, right? But IQ, somebody just made up this scale. Let's try to fit people onto a scale. And so what they did was they started with a bell curve and said they based the top, which means the most people would have an IQ of 100. And then it spreads out evenly there. So what that means is if you go over, I'm not exactly sure where all these numbers live, but if you go out to 130, right? Sometimes if you have an IQ of 130, they might tell you what percentile of Americans, let's say, or people that you're above. That's really what it means. But since that distance is 30, gets me up to that height, that means if I go 30 to the opposite direction and go up to that height, should be symmetric right there. Meaning, and I don't know if it's perfect, but this is the way that the numbers were designed to reflect, is that out of the population, let's just say America, the most people should have an IQ of 100. The amount of people who have an IQ of 130 should be pretty much the same as the amount that have it as 70. Right, so if you move in either direction, and then this tail, we call it, starts getting closer, shrinking down to 0. Remember, you've got your frequency over here. So the closer you get down to this horizontal axis, the lower the number is getting, the lower the frequency. Which means if you have a IQ of 160, right, that's exceedingly rare. There's very few people who have an IQ of 160. And if you go to the left, that would be equivalent to, that's 60 more. If you have an IQ of 40, right, that's very few people that would fit into that category. Okay, so you can have a bell curve. In the book, they talk about a triangular curve, right? So that's kind of obvious. They've got a straight line. Let me just back up, see what they called that. Bear with me. I know it's not exciting watching a video of me off screen clicking my other computer. A uniform or rectangular curve is just if every piece of data is exactly the same. Okay. So there we go. So we've got mode, we've got symmetry. There's something called a skewed curve. And to me, a skewed curve, the language, I've always kind of thought it was backwards, but I'm not a statistician. I'm just teaching the course, so whoever came up with this stuff. If I've got a curve that looks like this, right, versus a curve that looks like that. Okay. Both of these curves are unimodal, right, because they both have one peak. They are both asymmetric because one side is bigger than the other, right? So asymmetric, unimodal. This is what's called a skew. Both of these are skewed curves, all right? Skew means things are favoring one side more than the other. And to me, my interpretation wants to be, well, most people here, or most data would live in this area. So I might want to say that that's left skewed. This is actually called right skewed. All right. So if you don't like that, you're in good company. But just that's the way it is, right? That's the way these things are defined. And it's in terms of the tail. So we call this thing the tail of the data. Since this flat tail that's approaching the axis is traveling off to the right, then we call that a right skewed graph. And same idea. The tail is approaching the left, and so then we've got a left skewed distribution right there. Okay, so just take those guys for granted. That's what you've got. All right. Not everything has a peak, right? So this graph might look familiar if you ever watch the news about all the COVID-19, right? Flattening the curve. The curve looks like this, right? So that's kind of a right skewed curve like that. You can have skewed curves that don't turn around and come back down. You can have curves that just go up and up and up. So if I've got let me put it here. For left skewed, if I've got a curve that looks like this, right? That's left skewed because the tail lives to the left. So that is a left skewed graph. It's unimodal because it's rising only really in one spot, but it doesn't peak and turn back down. It just keeps rising and rising, at least from the data that we've collected here. So that's okay. And they call this a J curve, a J-shaped curve because it's sort of like the letter J. Right, so there we go. A left skewed J curve is that, and you can have a right skewed. I think they call it a backwards or reverse. A reverse J shape could be something like that. All right, so you've got a curve like that. The tail lives on the right, so we are right skewed, and then there we go. So no big deal. There was one question on the homework where they give you a stem and leaf chart or a stem and leaf graph and ask you to decide if that is I don't think they ask symmetry, but they ask, is it left skewed or right skewed? So how do you interpret that? You could like start plotting the data and build a histogram out of it. If you've got a histogram, you can read skew and things of that nature. So some of the homework questions are asking you, they're giving you histograms and asking you the symmetry. So just for an example, if I draw this, right, that is a unimodal distribution. It's symmetric because it's got the mirror image. And so you could sort of wrap a bell curve around it like that. So sometimes they do that. So sometimes these nice smooth curves are built from sort of concrete data that might live in there. Okay, so you can have a histogram that looks like that, and you can still talk about these modalities, the symmetry, and so forth. Alrighty, and so the thing that I was thinking about with the stem and leaf is you could count up the number of leaves within each stem and then create a histogram based on that. So maybe you've got a lot over there and something like this. Right, so if you had a histogram that looks something like that, what's happening here? Well, this is kind of like that revert or that J shape, right? The curve's kind of going like that. All right, so this would be left skewed because there's fewer pieces of data to the left. Fewer smaller bits of data, more large bits of data. So you could try to kind of create a histogram based on the stem and leaf plot, or else just kind of look through the plot and see where, you know, a really long set of leaves means there's a lot of data in that class. If you've got a bunch of leaves with only small bits of data or small amounts, they would refer to sort of these small little bars right there. So you can kind of interpret that. So the one that I looked at from the homework, I was able to sort of figure it out just visually without creating a graph, but you could do something like that. All right, folks. Pretty short video because pretty straightforward concepts here. Again, browse the ebook if you want to see their sort of artistic representations. But we're in a good spot. So this wraps up pretty much everything we need for homework number 1. And then homework number 2 will be posted shortly. Next week in class, we'll go over some notes and keep moving forward.